Alright, so we're moving forward, covering the material, chapter 6. It's about columns, in particular about stability of columns and buckling. A subject relevant to machine design. I have here an example of buckled connecting rods, buckle rail tracks, buckle nail. So when this happens, buckling, when we have a slender machine element that is subject to compression, and what it does is losing its stability, its shape. What you're seeing here are plastic buckling. An example of application where we have slender elements in compression would be for the Mark II pump jack. And in order to lift the sucker rod, which can be hundreds of if not thousands of feet long and very heavy, these two, they run in parallel. These two links are in compression, and you would be concerned not to buckle them. Regarding the connecting rods, I would point to the way they are supported at the ends. So this connecting rod buckled in the transverse plane, and as you can see, so here was the crankshaft, here's the pin, a piston pin, and the slope of the bent connecting rod is non-zero. So if I have, let me be more explicit. If I have a line that connects the centers of the pin joint and of the the piston pin and the connecting rod, I have the slope. So I follow like the direction of the bent piece, and here too. So I have an angle that is non-zero. Contrast this with so let me open the other one. Open with and paint. Okay, so contrast this with this other example where so if I connect the line with a line, a straight line. If I connect with a straight line, the axis of the crank shaft and piston pin, as you can see, it's the slope right at the pin and at the so let me use red. It's zero. Okay, so there's no rotation, and then it started to rotate. The stiffness, the geometrical stiffness of the connecting rod was chosen to be less because of the way of the supports. Okay, they impede rotation of the ends. So for that reason, the connecting rod was slender in this would be the longitudinal to engine plane. The other example we had, and sizes are different, so I could, can I scale it? No. So here the geometrical stiffness is more because of the pin and the connecting rod allowing for rotation. So this will be more prone to buckling for a round cross section, more prone to buckling in the transverse plane than longitudinal plane. To best use the material, the connecting rod, like I said earlier, is slender, yeah, I could call slender. The geometric stiffness is less in the longitudinal plane. Okay, so let's move to the let's move to the chapter and see what the author said. It's easy to run tabletop experiments about buckling. Just take a slender ruler and apply compressive longitudinal forces, and you'll see that it buckles in would be X plane for this arrangement. If it's simply supported here, possibility of rotation, and here you push it with your palm, say, and allow again for a slope to be other than 0 at the end. All right, so when it comes to analyzing for buckling slender, that is columns or machine elements that are subject to compression and have a slender geometry, we can experience two instances, and we looked at some photographs, and I said all these are plastic deformation. They are not reversible, non-reversible, and when they occur, there's yielding and plastic deformation. But with the slender, ruler, if you're careful not to apply too big of a force, it comes back to its original shape, and that's going to be discussed first. It is elastic buckling or Euler buckling, and buckling depends on cross-sectional area, depends on the moment of inertia. Moment of inertia about an axis transverse or perpendicular to the buckling plane. So here, the moment of inertia about the y-axis proved to be, and given the end conditions, the way the beam is allowed or the column is allowed to rotate or not, so it was less than about the x-plane. Specifically, we're going to use what is called radius of gyration. It's the square root of the moment of inertia about the respective axis transverse to the buckling plane, divided by the area of the cross section. And we also learned that we looked at the example with the connecting rods. So it matters how you hold the ends, whether they are allowed to rotate, to pivot, or not. So the two connecting rods or two buckle cases, they will correspond to, let's see, so although this is plastic range buckling, but the shape of the buckle column would be this one. So the possibility of rotating about pin joints, and the end fixity, it's called pin and pin. There will be an end fixity coefficient. It's called constant pinning, the end fixity or end fixity coefficient. It's considered to be one, whether theoretical or practical value. Practical values take into account any slack and imperfections, and as you can see, they are slightly bigger than the theoretical values. The other type of or possibility of buckling a connecting rod would correspond to this case, where no rotation was permitted at the supports. Okay, so zero slope and then increased, and here the end fixity coefficient is 0.5. The theoretical value is 0.65, and this will be the most stiff way of supporting a column. That's why the area moment of inertia transverse to the buckling plane is less in this case than the previous case that we discussed. If we have a pole that's encastrated, so bottom end condition is same as number B, and the force can move with the stay vertical but move with the end of the support, then we have end fixity coefficient of 2, or practical value 2.1. This will be the case when, say, you want to drive a slender maybe a rod, or think of a nail, slender nail into a board, and you're hammering it normal to the surface in which you will drive it. This will be the least stiff case of all listed here. And then we have a combination of the first two, where I have pin and an encastrated end, and the value would be in between the two as expected. Theoretical value K 0.7, practical 0.8. Okay, so with these end fixity coefficient, we can define what is called an equivalent length. So equivalent length will be 1. In this case, even says the base case for end fixity. Here is like having a rod that is or column that is half its length. Here would be like being twice the length and having pin ended. The ends being pinned, and here's 0.7. Again, a combination between these two. All right, so again, this is the equivalent length and captures the effect of the end support's possibility or not of rotating, that is sloping the neutral axis of the column. Okay, slenderness ratio is the ratio between the equivalent length, that is end fixity coefficient, times the actual distance between the supports, divided by the minimum radius of gyration. Why minimum radius of gyration? Because we can, like in this case, radius of gyration, remember, square root of moment of inertia divided by area. Area is the same, but moment of inertia would be much less about the y-axis that is about the x-axis. Okay. So slenderness ratio, again, is the ratio between the equivalent length and minimum radius of gyration. And without any proof, we're provided here with results. First derive obtained by Euler. So theoretically, and for a slender column, the buckling occurs when the axial load reaches this critical value, which is pi square Young's modulus of elasticity of the material of the column, and it's considered, of course, homogeneous, times moment of inertia divided by equivalent length squared. There are alternative forms of this equation 6.4. See it here, where the slenderness ratio was introduced, and critical, that is the load, compressive load that's causing buckling, equals pi squared modulus of elasticity times the area divided by slenderness ratio squared. We're assuming all the time that this force remains centroidal, that is keeps direction. It's through the axis, geometrical axis of the column. So when designing for buckling, we're not looking at stress. As you can see here, it depends only on the elastic properties of the material and not on the yield strength. Again, this is elastic buckling. You take the load and it comes back to the exact shape, not like the pictures that I presented. So there we want to specify an allowable load, which would be, of course, less than the critical load. The ratio of the critical load over the allowable load, this is the design factor. And in just a little bit, there will be a discussion about choosing the design factor. Okay. Now, if you start with a column like was this one, and you start reducing the length, and you calculate, I said that the yield strength of the material does not matter, but let's say we are evaluating the yields, the compressive stress, and related it to the yield strength of the material. Euler theory does not capture the effect of exceeding the yield strength of the material for short columns. So if you calculate the buckling force for a short column and then the critical force, and then you calculate the stress, the compressive stress that critical force, critical load can generate into the beam, you can get very large compressive stresses, and corrections are needed. And for that reason, the alternative theory for short columns, Johnson parabola, it's called, and the transition between the Euler buckling and plastic buckling, described by Johnson's formula, happen when the slenderness ratio has this value. That is, it corresponds to a compressive stress being equal to half the yield strength of the material. So this column constant, CC, column constant, the transitional slenderness ratio is square root of 2 pi squared Young's modulus over Young's modulus of the material. So now it depends on the material. And for steel, for example, we know that Young's modulus for most steel materials are very close or the same. So the column constant that's going to, below which, so if the slenderness ratio is less than the column constant, we're shifting to Johnson's parabola, departing from Euler's formula, which moves up and does not capture the potentially large stresses for short columns. And there, the critical, so for short columns, for which the slenderness ratio is less than column constant, the critical load is given by this equation. Again, no proof for it. So it's function of area, the yield strength of the material, slenderness ratio, yield strength of the material, again, and modulus of elasticity of the material of the column. Okay. So for analysis, this is a flow chart that I recommend you to bookmark it, and you research the problem. I make sure I identify correctly the type of end support, that is end fixity coefficients, and then you compute the equivalent length, LE, which is end fixity coefficient times the distance between the supports. compute the radius of gyration, compute the slenderness ratio, SR, equivalent length over minimum radius of gyration. And then to calculate the column constant, you would need, of course, Young's modulus. Young's modulus occurs in Euler's formula as well, but you would need yield strength also. And then if slenderness ratio is less than column constant, if slenderness ratio is greater than column constant, this is Euler buckling elastic range. If it is not, then we have short column buckles plastically, and you use Johnson's formula. Okay, the two equations. So say you have a design factor of 2, you can recommend the admissible load, axial load, as half of, so if this is 2, this admissible load will be half of the critical load. That's about it for the case where the load is applied, again, axially through the centroidal axis, or aligned with the centroidal axis of the cross section. Apparently you can get some spreadsheets developed by the authors. You can write your own and to expedite analysis. In terms of efficient shapes for columns, cross-sectional shapes, of course you need to associate them with the type of end supports, and I'm going back to these two figures, and you saw, because of the end fixity coefficients being different for buckling in the transverse plane versus buckling in the longitudinal plane of the engine. But in general, the cross sections that are good for or when designing with columns, with elements, machine elements, they're subject to compressive loading. Tubular section is one. Columns for buildings supporting roofs and upper floors or floors above, they're round. The most cases for the end fixity would be K equals 0.5. All right, because the ends cannot rotate. But you need to make sure. So understand the system that you're analyzing to make the right decision. Hollow square section, fabricated C channel with side plates, angle pieces, structure angles, braced I-beams. I-beams, that will be the case of the, I'm going back to, yet again, these two images. So if you're to section somewhere here, you immediately recognize an I-beam as a section. I-beam being one of the good uses, providing good use of the material in terms of flexural stiffness. Okay. There's a section on design. I keep on saying that if you know how to do analysis, you can do design. You just try different cross sections. Definitely you'll look up in catalogs, the back of the book, or other sources for moment of inertia, for radius of gyration, for area. And you can repeat the analysis and you get a cross section as you desire. Based on my experience with working problems with students, identifying the correct end fixity coefficients is the problem there. And remember, they are theoretical values and they are practical values. and then the M fixity coefficient can differ in one plane versus the transverse plane, and you will have to do the analysis for both. Okay, but otherwise you can take Euler's formula and you can solve for the required moment of inertia. And things are the easiest when you have a round solid bar as the cross section for your column. And likewise for using Johnson's formula, you can calculate. So here's the end result again. If you're using a solid round bar and the predicted type of buckling is elastic buckling, this would be the required diameter if you're given the admissible load, the design factor, and fixity coefficient and length. If it's a short column, a similar approach gives us the required diameter for a solid circular section. Okay. Of course, you can calculate both, and not knowing whether it's Euler or it's Johnson's, that is elastic or plastic buckling, and you're going to choose between the two the largest diameter. Okay. Next, the chapter discusses the case of columns that have pre-existing crookedness. So because of the long and slender and perfectly straight is not possible, we have if this pre-existing crookedness makes the column more prone to buckling. And there is this equation 613, which is a quadratic in the admissible load. We have the design factor here. We have the yield strength of the material. This PCR is the critical load according to Euler's formula. So you assume no initial crookedness A. You calculate a critical load, and then of course you need to know about the material, like what yield strength it has. You can see here Young's modulus, it is modulus of elasticity is not occurring, but it does implicitly with the critical load according to Euler. So yeah, you calculate coefficients of this quadratic, and you can calculate the equivalent, rather the admissible load when you have the design factor and everything else being given, like c, the distance from the neutral axis to the outside of the section. You can have a section that's non-symmetric, for example a C-channel with the flanges pointing either to the outside or to the inside. Anyway, so you calculate the two coefficients, and then remember this is plus, so you need to include the minus, and then this other one is C2. You calculate the admissible load, and this will be it. Okay, and then we can have a case where the load is not through the or in line with the centroidal axis, and so it's eccentrically loaded, but the column is straight. It's not a combination of eccentric loading and pre-existing crookedness. It's just so we have the buckled shape, and here story is a little bit different. The first equation that's introduced, 614, is for the stress at the middle of the column, where you have the maximum deflection. That's why L/2. So stress caused by the load, the compressive load, in the middle of the bar, and this is called the secant formula. So this is secant of this argument. This has to be or assumed units of radians. So what else we see? We see the eccentricity of the column E. We see C, the distance from the neutral axis to outside of the section. And it may or may not be the same in to the left or transversely, depending on the cross section, of course. Okay, so we have the load that's causing this stress occurring as a multiplier and also argument of the secant function. So this would be is not possible to solve it in closed form. You need to use iterative methods. First, the case where we have yielding, it's of some importance to us. So this would be the load, axial load, that's causing yielding. It's a repeat of this equation where instead of sigma L over 2, I'm saying yield strength in of the column material, and this is the load that's causing the yielding. Okay. We can define allowable load as a fraction of the yield, the load that's causing yielding of the material, by dividing by the design factor. And usually it's 2. There is a section where design factor selection is discussed. So we have the version of the earlier formula that said what is the required yield strength of the material when I have this allowable force and this design factor. The Young's modulus of material known, cross section is known, type of end support of the M fixity is known. Okay. So in addition to the equation that allows us to calculate the or relate the yield strength of the material to the admissible load. So that is you essentially apply this equation to choose the material. There's also, going with the first of the equation introduced, what is the deflection that is caused by that eccentrically applied load P. And so I have an eccentrically applied load P. I have maximum stress in the middle. Also the middle is the maximum eccentricity. Okay. I'm sorry, the maximum, I take that back, the maximum deflection. So from the undeflected, the straight column to the buccal column, we measure from the neutral axis, and it gets you the maximum deflection, Y max. And there's that equation that allows you to calculate it. Okay. Maybe this is also relevant in terms of, I don't know, appearance, aesthetics, or interference with side components and so forth. Okay, so this was about it for this chapter. We're going to solve some problems. As you can see, this material is like standalone new. It's not based on earlier no more circle, no load analysis, shear force, bending moment diagrams. So in case you want to, I don't know, build some strength and competence in solving problems, although recommendation is for you to, of course, do your best and master all the material. The chapter 5 and 4 are very important for machine design, somebody that wants to do machine design career. But otherwise, the column chapter 6 is pretty much standalone, and you should be able to master it after trying some problems. Okay, so I'm stopping here, and we'll have additional posts with problems.